Hello world! I'm Gladwin Ferdz Rosario from the Polytechnic University of the Philippines Institute of Technology. Today I welcome you to the detailed walkthrough of the components of a simple as possible or SAP1 computer, specifically the circuit displayed here. In this video, we'll break down each component of this 8-bit computer and show how they work together to execute a simple program. We start with the program counter, or PC. This 4-bit register keeps track of the address of the next instruction in the ROM. It works by incrementing after each clock pulse, enabling sequential instruction execution. It also has control signals like CP or counter enable to allow the value to increment and CLR or clear to reset it to 0. The read-only memory, or ROM, in the SAP1 is a 16 by 8 memory module storing both instructions and data in a hexadecimal format. Each address stores 8 bits divided into opcode, or upper 4 bits, and the operand, or lower 4 bits. In our example program, the ROM is programmed to calculate. The instruction register temporarily holds the fetch 8-bit instruction from the ROM. It separates the instruction into the opcode, which specifies the operation, and the operand, which is the data address used for that operation. Control signals like LI, or the load instruction, enable the transfer of data into this register. The controller in sequential acts as the brain of the SAP1, based on the opcode in the instruction register. It generates control signals to synchronize and manage operations. For instance, when the opcode is LDI, LDA, or load accumulator, signals like LA or load accumulator and MI, memory in, are activated to fetch data into the accumulator. Next, we have the memory address register, or MAR. This register holds a 4-bit address coming from the program counter. It acts as a bridge between the PC and the ROM by selecting the memory location to fetch the current instruction. The MAR enables the ROM to retrieve data or instructions corresponding to the given address. The accumulator is an 8-bit register that temporarily stores data used in arithmetic operations. For example, when the add instruction is executed, the data in the accumulator is added to the context of the B register. The result is then stored back in the accumulator. It is also directly connected to the ALU for these operations. The arithmetic logic unit, or ALU, is responsible for performing arithmetic operations like addition and subtraction. It takes inputs from the accumulator and the B register and produces an input-output. The EU, or enable ALU, control signal activates the ALU during these operations. The B register is an 8-bit register that temporarily holds the second operand for the ALU. For instance, during another operation, one operand is in the accumulator while the other is loaded into the B register using the LB, or load B register, control signal. The output register is an 8-bit register that holds the result for computations for display. Data from the accumulator is transferred to the output register using the LO, or load of output, control signal. This register is connected to the 7-segment display, which visually shows the output. Clock and clear. The clock generates a sequence of pulses that synchronize operations across the SAP1. Each pulse triggers a specific sequence of events like fetching or executing instructions. The CLR, or clear, signal resets all the components to their initial states, preparing the system for a new program. Finally, control signals like HLT, or halt, LI, or load instruction, EU, or enable ALU, and EO, or enable output, orchestrate data flow and manage operations within SAP1. The signals are generated by the controller or sequencer and ensure seamless communication between components. Now, let's see the SAP1 in action. Our program will first load into the accumulator using the LDA instruction. This sets the accumulator to 00000101. Second, add to it with the add instruction. The B register is loaded with 00001011, and the ALU adds to 00000101, producing 00010000. Third, subtract using the sub instruction. The B register is loaded with 00000110, and the ALU subtracted from 00010000, producing 00001010. Fourth, output the result using the out instruction. The value in the accumulator 00001010 is transferred to the output register and displayed. And finally, halt the system with the HLT instruction. This stops further operation. As you can see, the final result is 10, which matches our expectation for 5 plus 1 minus 6 equals 10. And that concludes our explanation for the SAP 1 computer. This simple 8-bit architecture is perfect. It's a perfect introduction to understanding the inner workings of computers. Thank you for watching, and I hope you learned a lot about the mini world of computers.